A standard six-sided die is being rolled 7 times. What is the probability that exactly 4 even numbers are rolled and exactly 2 5s turn up? Okay. So we're repeatedly running this dice rolling experiment, rolling it 7 times. So that makes me think about what we've learned about repeating the same experiment over and over again. Okay. Now, do we have a situation that is Bernoulli trials? Okay. Do we have 2 outcomes to our experiment that we're talking about? And at first glance, you might say, yeah, we care about even numbers and 5s. Okay, but if we think about a 6-sided die, you can get 1s, 2s, 3s, 4s, 5s, 6s. Okay, now, 3 of these would be classified under the even number event, or the even outcome. And, of course, we've got 5s as well. But then there's also getting 1s and 3s, and that's a third outcome. The others, the leftovers. So we don't have 2 outcomes to our repeated experiment. We've got 3 that we care about. Evens, 5s, and the rest. Okay. So we can still use what we've learned about repeated experiments, but we have to use the situation with multiple outcomes. We have 3 outcomes of interest in our repeated experiment. So it is not a Bernoulli trial because those use only 2 outcomes and have a very specific formula. So we're going to have to use the different formula, n. We're going to have to use multinomial notation, n1, n2, n3. And these will be the number of times that we get evens, the number of times we want 5s, and the number of times we want the rest. Okay. The various probabilities of those outcomes to the power of the number of times we want those outcomes. Okay, so we've got some numbers to work out. Now we can see we're running our experiment of rolling a die 7 times. So n is going to be equal to 7. Okay. n1 and n2, that'll be the number of number of evens and number of 5s we want. Okay, we want exactly 4 even numbers and exactly 2 5s. So that gives us 4 and 2. Okay. But in order for multinomial notation to work, we need all the numbers at the bottom to add up to the top number, which should be 7. Okay. So n3, we've got 1 outcome unaccounted for, so we'll have 1 of the other possibilities, either a 1 or a 3. We don't care which. Okay. We also need the probabilities. Okay. What are the chances we get an even number? What are the chances we get a 5? What are the chances we get one of the others? Okay. Now, it's a fair coin, not a fair coin, a fair die, okay, with 6 possible outcomes. They're all equally likely. Okay. 1 of the 6 outcomes is a 5. 3 of the 6 outcomes are even. And 2 of these sides are the other category. So we get a probability of 3 out of 6, or 1/2, okay, for getting an even number. 1 out of 6 for getting a 5. And 2 out of 6, better known as 1/3, for getting the other, the extra, the leftover category. So with that in mind, we can now fit this all into the expression and get the probability we want. So 7, choose 4, choose 2, choose 1. The important thing here is to line up the number of times you want a specific outcome with its probability. We want 4 evens, okay, and we know that the probability of getting an even side rolled with our dice is 1/2. Okay. 1/6 for the 5s to the power of 2, because we want 2 5s. Then 1/3 to the 1 for the others. And that is our final answer.